It's all your turn.
Fantastic. Thank you for your patience, everyone. It's been a trying day. I don't know if you guys were affected by the big AWS outage today, but it was all over the place. Apparently, my computer was not to be spared. Fantastic. I'm gonna go ahead and let me see. Hi, everybody. My name is Dr. William Weaver. You can see in my little tiny marquee there. I usually go by Bill, and I'm happy to meet everybody for the first time. We're going to have a little presentation today. We will meet again online in the spring, and then we'll be happy to host you at the University of Maryland Eastern Shore campus next summer, which will be here before we know it. So enjoy your school year because it's going to go quickly. My school year will go quickly as well, and then we'll be able to catch up when you guys get here. Um, well, if I press the share button, I pick the right screen and I share my sound. I do this. At the moment, I think I just have a lovely thank you Windows beautiful screen there. Fantastic. And what I wanted to do first was I wanted to everybody can see the screen. We good? You can see the PDF document I have up there right now. Just a thumbs up. We good? Fantastic. Wonderful. Awesome. So thank you for everybody for submitting your answers to the pre-workshop assignment. And because it's 2025 and I like to use AI as much as the next person, I read through them individually and then I took all of them and shuffled them into AI and asked AI to get me a summary, not an average, but a summary response to see where everybody is. And of course, I was delightfully not surprised, but delightfully happy that everyone had some pretty great insights as opposed to sort of what we are talking about today and what we're talking about in this entire Estema program. So I know you can see it on the screen and you've been reading along. Our first question was, what is STEM? Again, this is simply the heart of everyone's response. Innovation and practical problem solving. I love that. Fantastic. This allows me to know what sort of conversation we're going to have when we go through our presentation. And yeah, of course, there's an E in here for engineering. So I appreciate that everyone mentioned things like engineering, mechanical, civil, and genetic. And then we got into mathematics and data analysis. And then, gosh, there's also some science involved in there. So biomedical and architecture. Wonderful, fantastic. Um, because the University of Maryland Eastern Shore is a agricultural school, we don't just teach agricultural, but our history as an 1890 HBCU is as a agriculture and technology school. I teach, and so does Dr. Volkus. We both teach in the School of Art of Agricultural and Natural Sciences. So they're put together. So there's a lot of science in agriculture, obviously. And that's something that we hope to introduce you to over the next year with our Monday evening presentations and also over the summer as well to show you that there's a lot of things career-wise. So yeah, what does modern agriculture look like? Again, these were your responses, so thanks for that. A lot of GPS. Yes, we're getting into a lot of robotics now. A lot of automated systems that actually measure the soil and measure what we're doing. That's fantastic. And then advanced harvesting. I heard this fantastic statistics actually today. At the turn of last century, 1900s, in the United States, fully 50% of all of the jobs were in agriculture. So we needed food, we needed to raise food, we needed to ranch food, whether that is animals or plants that were fish. So back at the turn of the last century, if you turned to your left or you turned to the right, half of you would have been working on a farm or fishing or ranching. It was just what we needed to do to survive. So now it's of course 125 years later, and it turns out the number of agricultural jobs that we have, it's not going to zero. We still need to eat, and I like chicken nuggets as much as the next person. But what we're doing is we've totally upped our game using automation and robotics and science and engineering to do things very, very efficiently to get much better growing yield per acre and much more efficient ways to harvest things, say from the fisheries that we have, especially here at UMES in the lower eastern shore of Maryland. So the fact that that agriculture is now only 1% of jobs, it doesn't mean that no one works in agriculture. It just finds out that if you do find yourself leaning towards an agricultural career, it's going to be very, very high tech, which is kind of cool, where we get to go ahead and use a lot of the STEM things that we do in agriculture, which of course is where the term as a STEM A came from. Let's see here. Are different science classes connected? I love everyone's answer. Hopefully, this is how you have been introduced to science in the grades schools, not grade school like in first, second, third, but all of the grades up through 12th. Is that the different subjects of chemistry and physics and biology and earth science, they're all integrated. They're all part of the same story. We just need to figure out what aspects we need to look at. So I really appreciate that you're there. We are talking a lot about systems this evening, and we'll be talking about systems over the next year and next summer. Um, so yeah, a collection of interconnected parts that work together to achieve a common goal or purpose. That's fantastic, and that's what the majority of our little discussion tonight will be about. What is a system, and how do we use systems in STEMA particularly? And then this last one, I again not pleasantly surprised, as in I didn't think they'd get this, but I was really happy that this was the overall synopsis. Is that art and science are very, very connected. Some folks who are not familiar with STEM might think that in again as a student you may take classes in art or you may take classes in math and science and they would never mesh, but of course they are very, very integrated and we use them all the time. So I was very, very happy to see your responses were that things for that particular topic. So what I want to do is pull up my presentation here and maximize it. So yeah, an application of systems thinking is what this entire presentation is. Looking at your answers from the pre-assignment, you're already thinking the same things we're going to be talking about. Um, my goal this evening is to try to take vocabulary that you already know. I'm not going to launch into any new vocabulary. These are all things that you already are familiar with. You're probably an expert at most of these things. But the goal is that system to see how they integrate and how they fit together. Um, so this is where we're at. I'm going to push the button here. I can't see everybody on the screen here, but just raise your hands. Anybody know what this object is? I see one, I see two, I see three. Does everybody want to admit that they know what this is? Um, it's been a while since I've played Minecraft, but it is it dirt? I think it's a dirt square. It's sort of how you start Minecraft every day, or hey, you have a new world, you get land in there, you land in the game, and if you're playing not on demo mode, you probably need to start digging some things to make a shelter before the zombies come get you. So yeah, this is a good way to explain to other folks who aren't STEM centered what STEM is. We start with this Minecraft idea of a block. And then we say, oh, by the way, there are different types of blocks that we can have. And I think that's our dirt again. And I think that's wood. And over here is stone. And I think this is iron ore. They have different types of blocks. And we know that different types of blocks allow you to use their different properties to make things. And of course, again, almost everybody has played Minecraft. And if you haven't, no worries. But typically, what we do in Minecraft is we find those individual blocks, we find those parts, and then we go ahead and we find something called a crafting table. And the crafting table allows us to use a recipe. And if we use the recipe and we use the crafting table itself and we use a certain number of these different types of ingredients, then we can make all kinds of cool stuff or all kinds of cool inventions. And even though Minecraft might sound like a simplistic way to present STEM, the reason why Minecraft was designed is because it's the truth. It's not a fable. It's not the kindergarten version of something that needs to be changed once you get into college. It really is the true answer. We take individual parts and then we use a crafting table of some kind, whether it's a reaction vessel or happens to be a computer where we're programming things. We use some sort of mechanism where all of those parts are brought together. We follow a particular recipe, and then once we follow the recipe, we go ahead and we make new things. Okay. So this entire process, which is captured and described by Minecraft, is a technique or an idea called systems thinking, where we're going to think about how these things fit together. It's not something I've made up. It's something you can go ahead and you can Google and read about. It is an actual philosophical area of research about how these systems go together. And even though a crafting table is a fantastic way to talk about it, when we move over to something beyond Minecraft, we might use what this crafting table definitely looks like a cardboard box, but inside systems thinking, we're always talking about the box. And I'm fairly certain everyone has heard the term thinking outside the box or thinking inside the box. But this box metaphor, this framework of using a box, is something that has come from general systems theory and systems thinking. We had this first, and then Minecraft is a version of that. So we grab the box, and then what we can do with this box is just like taking different blocks. We could put the blocks, you can metaphorically think you're putting it on the crafting table or you're putting it inside the crafting table, but we put different ingredients, which is why they're called ingredients, not outgredients, and then we combine them. So those ingredients, there's that in word again, is simply called input. Again, this is not trying to tell you words that you don't know. We've all know what input is, but again, this is just how these things go together. We take whatever ingredients we need and we input them into the box. And then, metaphorically speaking, the crafting table is where we actually mix them. We might have to mix them in a certain order. In reality, we may have to blend them for a certain amount of time. If you're making chocolate chip cookies, you may have to add the flour first and then the eggs and then the chocolate chips. It depends on how these things actually go together. There's going to be a recipe for how long to mix them. That's going to be called the process. The process is usually inside the box. And then after we're done, just like a crafting table, the idea is, well, what did you make? What did you craft? And maybe you're crafting a special weapon, a sword or a pickaxe or whatever you're making. And of course, it sounds, when I read it, it sounds like the kindergarten version. It's not. You put things in, input, you process them, and then you put things out. It's called the output. So these are the actual words that we use in systems thinking and in computer science, talking about input and output, something that you guys are already familiar. Um, this process of using a crafting table, this process of using a process box and getting something out is where we put things together. We call that synthesis, or we synthesize. This is where we put things together. The synthesis sort of starts with systems, is how systems put things together. And then if we happen to go the other direction, if somebody gives us a chocolate chip cookie and we say, wow, this is a fantastic cookie. Oh, it looks like there's some macadamia nuts inside, but I didn't expect that. That would be that we took the chocolate chip cookie and we tasted the macadamia nuts, or we literally broke it apart. We can take an existing system or an existing synthesis device and then tease it apart and look in, again with looking inside, we can see what ingredients are actually inside of that. So if I go ahead and push this button over here, what that particularly is known as analyzing. So analyzing is to take it apart. We want to analyze what the ingredients are. And then once you know what the ingredients are and you have the recipe in the crafting table, you can synthesize things on the outside. And then I had asked earlier on, what is the relationship between art and science? It just so happens that science analyze Science is associated with this analysis. Science is the process of studying something and looking at the parts to find out what they're made out of, and maybe even studying the process. How did they get put together? But it's typically on this side of the box and in this direction. It's sort of going backwards in time. We use science to find out, maybe we do an investigation. Maybe there was a case where there was a forest fire, and we wanted to see how the forest fire was started. We would do an analysis of what we have to analyze to try to figure out how it started in the past. On the other side, when we synthesize things and we make new things, we craft new things based on the ingredients we have, and then we can ask our scientists, hey, how do you think those things go together? That's the opposite direction. Opposite doesn't mean bad. It just means one is, in this case, one is to the left and one is to the right. One's toward the input, that's science, and one's towards the output, that's art. So art is when we put these things together. You guys already know this because I saw on your pre-assessment that you understand science and art are the same thing, just two different directions. Science turns out to be very fact-based. What are the pieces? What are the parts? How do they fit together? And then art is when you take those pieces and actually make it. So pick an art. Maybe you're doing visual art. So go ahead and get some shapes and some colors. Maybe you're making music. Maybe you're a music producer. You're going to take notes, and you're going to take sound samples, and you're going to take beats and tracks and put them together. Depending on what you are getting back to chocolate chip cookies again, maybe you happen to be a fantastic chef or a fantastic cook, depending on how you want to define it. That's art as well. We call it the culinary arts. So art is putting things together, and science is taking things apart. And then this entire system of input, process, and output happens to happen in an environment. So the environment is simply just what's outside of it. We can talk about the environment being outside in the woods. We can talk about the environment being inside in the laboratory. We can talk about the environment being in the past, like what was the technology that we used back at the turn of the century in 1900. How did those 50% scientists get their things done? Or maybe we're talking future. Once SpaceX gets us to Mars, how do we plan on growing food on Mars? If the environment changes, we have to make sure that that's part of what we're analyzing. So all these things are very, very important. So what I wanted to do is, before we get into this huge map of how these things fit together, what are the parts, and then how do we use this crafting table? I had asked you on the pre-assessment, what are some of your ideas of where STEM is useful? And you guys hit this out of the park. I don't think you saw these slides before you took the assessment, but your ideas are right in there. I think each of these guys are about a minute long. I just want to make sure that we sort of understand where things are going. I'm going to mute myself to turn off my.
Introducing the Helio AG272 Agro Drone. The AG272 is one of the biggest drones on the market with 150-pound payload capacity. It's what we call Texas-sized. With easy folding for transport, you can set up and tear down in a matter of minutes. Customizable nozzles give you wide and consistent coverage for liquid applications, and the optional spreader attachment can be used for seeding or granular products. With streamlined refilling and charging in the field, you can spray all day with minimal downtime. The AG272 is designed to stand up to the elements and has no problem navigating complicated areas. The AG272 operates autonomously. Simply use our AgroSol ground control software to assign full coverage, broadcast applications, prescription spot spray treatments, perimeter passes, and more. Gimbal-mounted radar sensors automatically adjust in order to detect and avoid obstacles, such as trees and power poles at high speeds. The AG272 also uses radar technology to maintain precise altitude above the crops and terrain. A dual RTK compatible GPS system achieves centimeter level precision. The AG272 is equipped with high definition video streaming and manual control mode for ad hoc missions. But the real fun starts when you deploy a whole fleet of agro drones to knock out hundreds of acres per day. This isn't the future, this is now. Visit our website to purchase Helio Agro drones today. Elevate your farm with Helio.
Fantastic. So again, yeah, a lot of these YouTubes are commercials for the companies. I don't mean to sell anything. I don't know these companies. I just grab them. But again, thinking about what agriculture is in 2025, that is most definitely agriculture. And this summer, we have a large drone and flying drones component in the Astema program because it is something that we do. And beyond, and in addition to just taking pictures of what the field looks like to get an idea of what's going on, especially for a large field, as we just saw, increasingly the drones are actually doing the farming. The drones are applying applications of either fertilizer or pesticides. They can actually apply the seeds. There's all kinds of cool stuff that these drones and these fleet of drones are doing. So GPS is definitely a component. So let's see what this next application is.
Vertical farming is going to enable us to feed the world in a completely different way. Fresh, local food year-round.
There are several elements of technology and innovation that are coming together to enable this business model to be sustainable and successful. The ability to grow the crop with exactly what the crop wants for the result that the consumer loves. And we're taking away all of those miles of transportation and bringing to you fresh food grown locally in your community that was harvested hours ago, not days or weeks.
We have this closed data loop where we basically take all the data that we have that we are collecting during the growth process, environmentals, nutrition data, from the fertilizers, lights, pretty much everything and anything that might affect the growing crops. And then we develop predictive models so we can correlate what we observe with our input variables.
So I'm most excited about just the quality of the product, And in all the years that I've worked in produce, I've never felt like this connection to the product.
What I'm talking about here is not science fiction, it's not the future, it's not 5 years from now. It's today. It's also the only farm in a world that can grow tomatoes and cucumbers and berries in exactly the same structure.
We are open for business. We're ready to go. We're ready to build farms in a community near you. So if you're wanting fresh local produce that tastes great and is pesticide free, is grown in a sustainable way, call us.
Fantastic. So as we saw that little tiny vignette, lots of technology, lots of computer science, lots of data analysis. You simply heard the person at the end saying, if you'd like your food pesticide free, you guys are familiar with what pesticides are. Aside means to kill, and pesticides kill pests. But if you're growing your food inside a building and you don't let the pests in, then you don't have to worry about killing the pests that are on your field. But if you are outside and you're growing something really tasty, it turns out that insects and animals and all kinds of other things, they think it's tasty too. So unfortunately, you have to do something to make sure that other animals and life forms that share this earth with us, share the planet with us, don't eat the food before we get to it. So unfortunately, sometimes we need to do some sort of pesticide remediation where this doesn't happen to have to happen. Okay, I have one more short little video here, and then we're
Agriculture is in a state of radical change. farmers are looking for new methods to make the cultivation more sustainable. Berry can be part of that solution by harvesting safely, reliable, and all day long. Plantability and labor shortage are some of the major challenges in strawberry cultivation. Growers are struggling to find the right amount of harvesting workers in the right time of the year and with the right skill set. As strawberries are a very delicate fruit, sometimes one touch can be too much and increase the risk of molding and reducing the shelf life. Berry is able to navigate through the greenhouse fully autonomously. It's driving through the rows, shifting rows if the row is empty, and pick the right fruits at the right time. With its image recognition software, it's able to determine which fruit is currently suited to fit to the grower's individual needs, depending on the season, on the time of the year, and his customers. It picks the fruit right at the stem, not touching the fruit, which limits the risk of reducing the shelf life due to damage. After founding the company 2 years ago, we are now a team consisting of 10 people working in fields like hardware development, software development, image recognition, but also fields like marketing, sales, and business development. From the beginning on, we involved growers into the development of our product and listened to their needs and requirements. By doing this, Berry can now be very easily integrated into current greenhouse situations and work with all the other harvesting workers. Berry can be your next step towards the agriculture of the future.
Fabulous. So for that particular video, we just saw a bunch of robots for harvesting. I mentioned earlier that in 2025, around 1% of the jobs that humans do are in agriculture. And of course, we think about farmers, we think about the people who are actually doing the seeding and the planting. And if you can't harvest it with a giant machine, in this case, it requires very delicate picking. If you don't have 50% of your population ready to pick the fruit, and the fruit's only ready and ripe for, say, a few weeks out of the year, that turns into a really huge problem of where we're going to find enough humans that are trained to pick the crops and harvest the fruits and harvest the vegetables correctly, so robots can solve that problem. So that's why we do that. So this idea, so again, that just gets us ready for what are we talking about when we talk about agriculture, and why is there science involved, and why is there engineering involved, and why does it involve drones and robots and computer science in addition to chemistry and physics and biology. And all of those things that I keep throwing out there, rather than just saying S, T, E, and M, they all fit on a particular map. And the map happens to be how we organize these individual components. And that's what I wanted to take a look at for our next few minutes. Okay, so we're already halfway there. So here's this box again. Again, we're going to start with this idea of a box. I'm going to switch my finger here. So this story, systems thinking, agriculture, the entire story is very human-centric. It is a human story. Yes, we can talk about the dinosaurs, and yes, we can talk about the planet. We can talk about the birth of the universe billions of years ago. But what we're talking about now is very much a human story because it involves us. So yeah, there's our components. So just like we had a crafting table before, and we could use blocks of wood or blocks of stone or blocks of iron, not to turn humans into blocks, but our ingredients now are humans. And so crafting table wise, when we take humans, if everything is working properly, hopefully we get more humans. If we put humans together, we can craft more humans. And when we do that, the art, if you will, is that the humans themselves start building societies. So in addition to parents having children, when you have a bunch of parents in a local area having a bunch of children, they start organizing into a larger community, if you will. And of course, we're going to call that a society. So this is something that you already know. We take courses in them. We take classes in it. And what we produce is, depending on how far you want to go back, maybe we talk about ancient human history where we have tribes, if you will. But now we have tribes that are different sports fans, obviously, but in addition to that ingredient of those humans who are related by kin or that happen to be related by where they live, we also have they produce culture, and as I'm reading here, they start trading with each other. We start developing business. Sometimes we need to decide what we're going to do, which side of the road are we going to drive on, if that happens to be important. At what time in the day should we be open so that it's open for everybody to show up? We need to have some rules, and typically that involves some sort of governance as well. There are different systems for doing that. So there's all kinds of things we can study when we talk about society, but just like the crafting table metaphor, when we have a bunch of humans and we get more humans, whether they're on an island or a continent, we have to sort of figure out how these things work. And that gets into our society. And then entire societies, and you guys have started to study, I'm sure you're probably through a lot of your US history, your ancient history, medieval history. We start getting this idea called philosophy. Got different cultures produce different philosophies. We have Eastern philosophy, we have Western philosophy, and this is where this comes from. So we need the society to generate these ideas of how we go about doing things. And it turns out that STEM happens to be a framework. It's a philosophy as well as how these things go together. So this is where these types of things emerge. Again, crafting table wise, when we have a whole bunch of people doing different things, they find out what works, and then it turns out that they get a particular philosophy. So if we take these three things, and this is great, we could be done. We could say, oh, by the way, we have humans, and then we have humans that live together, and maybe they're nomadic, or maybe they go ahead and they put together a little tiny culture, and they have a philosophy, and we probably, as humans, existed this way for a while. And then after a while, we started to branch out. We started to branch out our understanding of, hey, how did we actually get here and what makes humans humans and all these other things. So arrow-wise, we're heading backwards again. I mentioned before that art is sort of in this direction. That's where a lot of, but this way we're going backwards. And it turns out that some of the people who were up here in these disciplines and these study, they said, you know what, I'm going to go back and study where humans come from. So we got a bunch of volunteers, and they were philosophers. And it just so happens that the philosophers that were not looking to see where we're headed, these were the existentialists, that the philosophers were looking backwards, they got a new nickname. And of course, that nickname is scientists. So in our Western tradition, if you are a scientist, you're a philosopher who likes to study things, study wisdom, and typically you're facing what things are made out of. What's the ingredients? So if we ask that exact question, okay, great, we know that philosophy had its ingredients of society, and we had society, it has ingredients of humans. Of course, we have to ask the question, what are the ingredients that we need for humans? If I push these buttons here. Before I do that, I forgot that I had this guy sitting up here. Those scientists that we charge with going backwards, we often give them or deputize them with a degree called the Doctor of Philosophy. So it's a philosophy doctorate. So many of the professors that you're going to see, or maybe you already see them in your high schools, many of the professors that you're going to see at colleges and universities, they're going to have a PhD after their name. So the PhD, we call them doctor because they're doctorates. The PhDs, they're philosophers, but I thought you were a scientist. Well, not to be too confusing, yes, I have a PhD after my name, but I'm a scientist. I introduce myself as a scientist. It just means that I'm a philosopher that happens to look backwards. There are other philosophers that do other things. So yeah, the quick question is, where do humans come from? Well, we can think about that, globally, but what we can do is the way we organize this, and you guys have taken biology in high school, is we can definitely recognize that humans are part of a cadre of items we call organisms. Okay, so yes, so we happen to be an animal. We happen to be mammals. We're not reptiles. We're not insects. We're not crustaceans. We have different kingdoms. We have different families. All of these words that we use were developed by scientists who were studying where humans come from. So all I did was I went to higher order animals the whole way down to bacteria and viruses. And then the question is, where do the organisms come from? Again, going back to this idea of, great, these animals, and even these viruses and bacteria have parts. Where do those parts come from? And of course, if you have an organism, which is a collection of parts, we can call those parts organs. So this is all the things that you've studied inside life sciences and biology. Many of the organisms share these parts. Many of the organisms we're talking about have brains. Bacteria and viruses, as far as we know, don't have brains, but the higher organisms do. And then maybe leaves and roots are only there for plants and fungi and mold, depending on how they produce. Where do the organs come from? You already know the answer to this because you've studied biology. Again, going to the crafting table, cells, the individual cells. We have a heart cell, we have eye cells, we have liver cells. Those cells, crafting table wise, they band together and then make an entire organ. So if we sort of back out here and we look from the art side of things and go back to the crafting table analogy, we can say that the cells organize into organs, even use the word organize, and then the organs organize into organisms. This is where we get humans. And as scientists, we like to label this, we call these the life sciences. All of these things, as far as we know, are alive. Maybe viruses aren't alive, but they're all part of the life sciences. And since we've named these three things, we should probably name these three things. We're going to call these guys the social sciences after society, or we're going to call them the humanities, or the human sciences after the humans. So if you have been to a college class, or you're taking an AP class in society or social sciences or humanities, that's where these guys come from. But of course, we're not done. We have to go backwards even more. Where did the cells come from? So we have to keep on going. So it turns out that there are ingredients that go to the crafting table to make cells. And one of those things happens to be information. It's very generic. It's patterns, it's structure, it's instructions. You guys have studied enough life sciences to know that DNA, deoxyribonucleic acid, is a set of instructions of how we build living things that contains that information. Where did the information come from? Well, before we can make patterns out of stuff, we need stuff. So then we come back here and we get material. This is the stuff that we can organize into different patterns. So now we're specifically talking about things that we get Minecraft for. So this is where we get our metals and our stone, and in this case, our ceramics, or the wood. Polymers would be wood, the metals would be iron, and the ceramics would be stone. And then we can go even smaller and get atoms and molecules. And then once we have those items, our last thing here is energy. So in Minecraft, you know that you can use a crafting table to make things explode or calculate or open or close. You need a way to do that. We're all the way back to force and light and the like. Our last three, every three is a wonderful number. We get our three. We're going to call these guys the natural sciences because we found them in nature, or they're the physical sciences. We can physically touch them, or it happens to be that maybe we're talking about physics. So when you visit a college, or when you're headed to college and you have these classes in high school, maybe high school does not have to go to, I have to go to energy class, or I have to go to material class, or I have to go to information class. We just happen to have different names for these things. You guys already know this. Physics is the study of energy. We call it physics. So you can be a physics major and study energy. Chemistry is the study of material or stuff. Mathematics is a study of information. Computer science or computer math is part of that. Another version of that is called informatics. And then we keep on going. Oh, by the way, what if I want to study cells? We call that cytology, or the genetics of how the cells actually get built or work. How the organs, where are they? How big are they? Where would you find them? How would you fix them? That's anatomy and physiology. And then the organisms themselves, the different kingdoms and the different ways that things, food webs and the like, I'm just going to call that generically biology. And then we have to keep on going with the final three. We need names for those as well. And this is what we do as we're arting through this. Humans, to study humans, not only we have to study their physical bodies, we need to study what makes them tick, their brains. So, of course, that's psychology. If they get ill, we'd like to repair them. That's going to be the study of medicine. Society, we're going to call it sociology. We're going to study why people do what they do. Ethnography, where do different peoples, where do different tribes come from? And then how do these different tribes and peoples and ethnic groups, how do they conduct business? How do they trade? That's economics and management. And then if somebody happens to drive on the wrong side of the road, we should probably have some laws and figure out who's right and who's wrong and who's responsible. And then we can specifically get into even higher areas of philosophy. You don't have to be a PhD and be a scientist. You can be a PhD and just be a philosopher. And that's where we do things like studying politics and beauty, aesthetics, and ethics, how we behave ourselves. This entire process, here's the map. So the map, according to our human map, it starts with the physical and natural sciences. There's no humans down here. And then we believe either you think of being created or some sort of intelligent design, or it just happened by the way that we provided through. We don't need to have a particular explanation. But then we go through the life sciences. All of a sudden, life emerged as we kept on crafting things. And then eventually we got into human society and philosophy. So this is almost Minecraft from the very beginning, day one, the whole way to making an entire world inside Minecraft. But of course, we call this the universe. We call this the human universe or the university, which is where we study things. So all these topics, you go to a university in order to study these individual components and then place them together. So we're going to take a look at it real quick. We're almost finished here. Is what if we take physics, chemistry, and mathematics, and rather than just say, yes, I get it, I want to play Minecraft, and I always want to build the same thing. I'm going to take physics and chemistry and mathematics, and I'm always going to build cells, and then I'm always going to build organs, and then I'm just going to build new people. So I'll make Bob, and I'll make Gary, and I'll make Susan. That's great. It's a fun game. But it might be a more fun game if you can create new things. So to create new things, we're going to go off this track. We're going to go off this line and go into where we're going to go off the designation. We're sort of going to sidestep it and go to the side and see if we can't make additional, different, new things that we craft using the crafting table, that humans specifically, using their brain and using their crafting tables and using their know-how, using their science, we can take these primary ingredients and we can make new stuff. So it turns out, again, following this pattern from the left to the right are what artists do. We take ingredients and then we make art. We use paints, or we use dance moves, or we use notes, or we take ingredients. It turns out that I'm going to call these guys, or these folks, non-linear artists because they're no longer on the main line. They've sort of sidestepped it. And it turns out that one of the older words for this, I don't speak French, but I believe this is a French word, ingénieur is what it's for. It means that this term is gifted with genius. Like, what a genius idea to take those ingredients and invent something different. And in 2025, we call those folks engineers. So yes, you can think of an engineer is associated with an actual engine in a car, or the engine like Thomas the Tank Engine that pulls the train. That's one way to think of an engineer. But the historical definition of an engineer is someone who is gifted with genius and can make new cool things, and invent their own crafting table and make inventions for us to be able to use. Okay, so what are we going to do? Well, we're going to grab the crafting table. We're going to put together a design of how you need to do it, and then we're going to define what we need as input. And our input is going to be different flavors of energy, different flavors of material, and different flavors of information. We're not going to spit out cells. We're going to spit out cool stuff. And that cool stuff we're going to call technology. So you guys already know this as I'm preaching to the choir. Here is the Greek term. I think if it, so techne is how I pronounce that. So there's a tau, there's an epsilon, there's a chi. Fantastic. So this word in Greek means art, skill, or craft. So again, Minecraft. The technology is that which we build using art, putting it together, skill, a skillful engineer, and or crafting on a crafting table. So this is the word that the ancient Greeks used. They didn't have, as far as I know, they didn't have computers to run Minecraft, but they've been talking about Minecraft since that ancient civilization in the Mediterranean. So this is my modern version of what this technology stands for. Is engineers are artists that paint with science and math. So science and math, energy, material, information, the science part, and information, the math. This is the ingredients that they use. And again, they're crafting, they're painting. So again, your correct assertion that science and art are really, really closely related. It's exactly the case when we talk about engineering. So we're almost there. So yeah, science, hooray, STEM. We're finally here as far as defining this map. So we're going to take science, engineering, and mathematics, and we're going to put those together to make technology. The question is, what type of technology do you want to make? We can make humans. In fact, we're making synthetic organs and cells. But for now, this summer and over this year, we're going to be talking about using this crafting table to make new technology for our agricultural folks. So yeah, if we go to Wikipedia and we look up what is agriculture, it is the art and science of farming, hooray, which is cultivating the soil, the growing of crops, and the rearing of animals. Fantastic. Maybe the rearing of animals is the collection of animals, say fishing as well. But again, there's art and there's science. The art and the science go together. The science is what makes it work. What are the ingredients? The art is how do they actually put together. So what I'm going to do is I'm going to take this energy, material, information and sort of run it down this arrow down here. What are we talking about? Well, we have an entire area of research that we do here at the University of Maryland Eastern Shore called environmental sciences. So this environmental science is not particularly about humans themselves and animals themselves, but of course it is their environment where they live. We're going to be using this technology to make new farming equipment and robots. And then we can take anatomy and physiology. What are the parts of a particular animal, or what are the parts of a particular plant? And then that's going to take us into something that's called ecology. Again, ecology is how the plants and the animals and the environment live together. We have plant sciences at UMES where we're studying the individual components of the plant. How do we craft a plant? How do we make them better or well if they happen to be sick or they're attacked by pests? We have animal sciences. We're building a brand new veterinary school here at UMES. Again, with the idea of studying animals as part of this ecology study. And then we have marine sciences. Hopefully, if you haven't been to the eastern shore of Maryland before, we are surrounded by the Chesapeake Bay to the left, and then the Atlantic Ocean to the right, and a couple other bays, Ocean City Bay. Right next to us, we have a lot of water around us. It's sort of like the northern version of Florida. So we have lots and lots of ecosystems that have to do with fisheries and studying how ocean systems and bay systems and aquatic systems work. And then, of course, this last thing's here. So if not the sciences, then the ecology. What about these guys? What about things that we study from these top threes? What about economics and management and law and business. That's where we get into exactly that. Agribusiness. How do these things go together? How do we ensure a profit? How do we make our farmers make sure they make enough money that they can pay their workers or invest in new technology? That's agribusiness. We also want to worry about food safety. We want to make sure not only is the food nutritious, we want to make sure that it's healthy. If you've ever unfortunately had a bout of food poisoning because something got spoiled, we need to have science and technology that can tell us if our food is contaminated with a bacteria like salmonella, or if it happens to be spoiled. We don't want to eat bad food. There's, of course, the ethics part, which is the philosophy part. Even though we raise certain animals for consumption, for food, we want to do so ethically. We don't want to, we don't want to have an amazingly bad experience for the animals. We want to treat them ethically and realize that they're living human beings before they're consumed, unfortunately. And then there's also the logistics of how do we get our products to market. It may be that we grow a lot of corn and soybean here by the university, but maybe our folks who need it, or maybe the animals that consume it, are either somewhere else in the United States, or maybe they're even over in Europe or in Africa or even in Asia. We sell these things, and the question is, how do we get our products to them timely and least expensively? So all of these things are things that we can discuss, and we can study all this stuff as part of agriculture that has components in the first three: the physical and natural sciences, the life sciences, and the humanities and the social sciences. And that's all part of agriculture. And of course, we do all of that because we are a university. We do all of that here at the University of Maryland Eastern Shore. And again, just a little advertisement wise, this is studied inside our School of Agricultural and Natural Sciences, and we have sister schools or sibling schools inside our university that study engineering and the business components of this as well. Fantastic. So that was me talking really quick to make us hit 9:30 because I know we started late. I'm going to stop the share. Fantastic. And I am back. Wonderful. Sorry for screaming at you because I wasn't able to get your response. When we meet each other face to face this summer, we'll be able to have a conversation, not a better conversation, but conversation at all, as far as answering your questions or getting your ideas behind things. Fantastic. Ms. Gravenyook, thank you for the opportunity. This is fantastic.
Thank you very much.
Thank you.
Thank you so much.